On the very first part of your friction sheet, if you look at the top, you're going to see a bunch of formulas, right? We have our net force equaling ma. We use that for when an object is accelerating, and then you see your two friction forces. Maximum force of static friction is equal to coefficient of friction, which was that mu letter, times the normal force. And then if we have a surface that's sliding, then that's kinetic friction. Looks the same, only we use a subscript of a k instead. And then we always know that if we have an object, we can know its weight or its force of gravity, the downward force acting on it. These are really the only forces we need for this activity here. And if you look at the front of the sheet, you see a guy pushing forward with a force that way, but then there's a force of static friction that way. Remember, when we learned about static friction, we said that the force of the person is going to push forward. Friction may or may not be able to cancel out whatever they do. And this is a variable force. It can grow and grow and grow until it doesn't grow anymore. So essentially what we're seeing here is that, we gradually step up the force of the person in that table. At first you see that it's 5 newtons forward for the force of the person. And what we would expect is that, well, since there's no movement, and we're told there's no movement, essentially you have an acceleration of 0, which means that F net is 0 as well, meaning the forces cancel out. So I would expect the force of friction to be 5 newtons the other way, and so they match, and you get no movement. When we push with 10 newtons, we're still going to get no movement, and so again, acceleration, net force is 0. And then what we're going to do is, when we do the 15 newton force, we'll say, well, friction is still strong enough to push back with 15 newtons, but this is going to be our limit. If you look at the picture of the guy saying friction can't push back any harder, that would mean that this value right here is F of S max, and that's the highest we can go. So the net force is still 0 here, the acceleration is still 0. So in all three of these cases, you got A equaling 0, F net equaling 0. But now, once we exceed that maximum force of static friction, we have our guy pushing with a 20 newton force forward. Friction's still only going to be able to push back with this. So do the forces cancel out? They do not. So F net, you could write greater than 0, you could write it's not equal to 0, and then you would definitely get movement in this scenario here. So that's what you're going to see. And in example problem number 1, we're given a little bit of information here. We said that there's a 40 newton force required to get a 5 kilogram box to move. But then once it's moving, we only need a 30 newton force. So essentially, we need to apply a 40 newton force to get it to move, meaning that there was probably a 40 newton force of friction, and we're going to label that as F of S max. Because once we go just a little bit beyond 40 newtons, it starts to move. But then once you get it to slip, turns out we don't need as much force anymore. 30 newtons is enough to keep it moving, because just like in lab, what you're doing is you're balancing out the force, and if it's already moving at constant velocity and acceleration is 0 means it doesn't speed up, it doesn't slow down. And now it's sliding, so this is kinetic friction in the second scenario. So question 1 is kind of like 2 questions in one. And essentially, we know our F of S max value is 40 newtons, our F of K value is 30 newtons. Now there's 2 other forces here. There's gravity, there's normal force, and this is a 5 kilogram object, meaning if you look at the force of gravity here, it is 5 times 9.81. And that's going to give us 49.05 newtons of downward force from gravity. After that, we have a 49.05 newton force from the normal force, because these two things typically are balanced here. Now what that allows us to do is essentially calculate the coefficient of static friction, because if you look here, we have a value for F of S max, we have a value for the normal force. So if we look at our formula, F of S max equals mu s times n. We know that this is 40. We know mu is unknown right now, and we know that the normal force is 49.05. So once I do 40 divided by 49.05, that'll get me my coefficient of static friction. So mu s is 0.8155. Now you would do the same thing for your kinetic friction. essentially. We know that the force of kinetic friction is 30 newtons. By the way, over here we still know that the normal force is 49.05. So if I do Fk equals mu Kn, this is 30, mu K is unknown, this is still 49.05. You're going to find that kinetic friction is always less than static friction. So I get a coefficient of kinetic friction of about 0.61. So that's how you want to approach the front part of the sheet. And hopefully that's enough information to get you started. What you're going to see is that as you go further throughout the sheet, on the very next page, there's a table for you. And it's a table of values of mu. So you have a whole table involving a set of surfaces, and then we give you your static friction values, and we give you your kinetic friction values for mu. Again, if you look at those mu values, the kinetic's always less than the static. So what's going to end up happening is that in each of these problems that I've given you, you're dealing with a few surfaces. And for example, if you look at problem number 5, it's going to say you've got a wooden box on a wooden floor. Well, given that piece of information, I want you to go back to your table and look at the mu values. I'm seeing 0.5 for wood on wood for static and 0.3 for kinetic. If you look at maybe another problem like number 7, you've got a car. Keep in mind that car's tires are made of rubber and it's on concrete. So maybe we would go back and look for rubber on concrete, which you're going to see in the tables 1.0 and 0.7 respectively for those values. So I think that might be enough information to get you guys started. Just really quickly, I want to show you that if you turn to problem number 9 really quickly, you'll see a guy pushing a box, 30 kilograms. What you're going to find is that he's pushing it at constant velocity. You cannot forget that constant velocity means that A equals 0 and all forces are balanced. So if we give you his forward force, you're going to see that his forward force is labeled or given to you in the problem as 35 newtons. What that also means is that since your forces are balanced, we're going to have a 35 Newton force of friction as well. So it's not obvious to everybody, but there's your sense of direction there as far as that problem goes. In the very next problem, what you find is that it looks like a very similar problem, only we are told that this thing is now accelerating at 3.0 meters per second squared. That means it's not balanced. So you guys had some experience with the most recent sheet that you handed in to me with unbalanced forces. In a case like this, I think we ask you to determine a few things here. We're told that the forward force is 110 newtons, but this reverse force kinetic friction, it's unknown in this scenario. So you're probably going to have to use F net equals MA to get the net force. And keep in mind your A value is right there. And then once you know the net force, you should know that this force is greater than this force, which allows you to ultimately determine what the force of kinetic friction is. Alright, so hopefully that gives you guys enough direction to get through this worksheet that I've posted for you.